Okay. All right. Let me see. Okay, so where were we? Right. So we were at the point where we had where we were going to start changing this B section, shifting things to the GPU, right? Okay, here we are. So continuing from there, these two lines here will allocate the two arrays that we want on the GPU, and we're going to allocate the arrays and store the pointers to that GPU memory in these two variables, dx, pointer variables, dx and d_x and d_y. Okay, so this has to be done somewhere here. And then we should not forget, before we leave this section, to free them, somewhere here, right? Okay. Okay, so what do we have so far? Just allocated these two arrays on the GPU and freed them down here. Now we need to make sure, so now we have allocated but uninitialized memory on the GPU. And so now what we want to do is copy x1 and y1. So that's where these random numbers that we initialized and are going to operate on are stored. We want to copy these to the GPU. So we need to use this CUDA memcopy command. And remember that the direction now should be this flag here, host to device, right? Host to device. So that can be done right here. Okay. So what have we done so far? Allocated the two arrays on the GPU, copied the memory from the CPU to the GPU with these two lines. And now is when the magic is going to happen. We will now not call this ax plus y, axpy function, which runs on the CPU, but we're going to invoke the new CUDA kernel that we wrote, which is called GPU axp, right? So we call it like this, GPU axp. But of course, we need to decorate it with these, I don't know, chevrons, I don't know what to call them, greater than or smaller than signs. And for now, we're going to use one block, one thread, okay? So just one thread, 1, 1. But remember, the GPU kernel now can only access GPU memory. So what we need to pass to it, to this GPU kernel, are the pointers to the GPU memory, right? So these have to be dx and dy. Okay. These dx and dy, remember, they were returned by the GPU alloc, which allocates memory on the GPU. And the last thing we want to do is copy back from the GPU the resulting y1, because in the end we want to compare this, right, with what was done on the CPU and make sure that we get a difference of 0. So this has to be done after the operation concludes. So somewhere here, right? Okay. Okay, this bit is not important. Well, depending on how picky you are, this might be important for you, but we should change this line so that it doesn't say CPU, right? So that it says GPU now. Because this reports the time it took to run it on the GPU. Okay. So if we're all at this point, we can compile and run. Yeah, we don't need this stuff. You're correct. Because we're not reporting the number of threads anymore, of CPU threads. So you can clean this up, but it won't matter whether you do or not. I mean, it's okay. Okay, I am ready to run this now. Compile as before. Shouldn't need to change anything unless I made some syntax error. No. And then I run it. And now remember, the first part will run on the CPU as before, but the second part now should be the new part that I wrote to run on the GPU. Let's see what it says. Oh. What did I do? I forgot some switch. Okay, that's where it works before. There's not the size. Why would it? Sorry, I don't seem to understand what the problem is now. Oh. Minus, maybe it's this, but I doubt this will be it. Sorry, I just need to understand this for a second. Okay. So it seems like the CUDA compiler is defaulting to a later version of the GPU. And that's why we were getting this error. So you need to specify this option -arch SM_70 when you call NVCC to say that you're compiling for the specific version of the GPU. Okay, that was the problem. That was what was not in the slides. Apologies for that. Just let me just make sure that this was indeed the problem. No, not that. So as I said, we add so what I put here is what you need to type in. So you need to add, oops, now it's gone, sorry. You need to add -arch SM_70. Okay, this specifies the version of the GPU that you're going to run on. Yeah, apologies. I guess the version was changed, of CUDA was changed, and now the default version is a later version. Okay, which is why this didn't work anymore. Okay, and if you call this srun command, okay. So what we'll see now is some huge number for the bandwidth, which cannot be true, right? Cannot be accurate. And so what is going on? This is also on the slide. So you get something like, you know, huge. Well, okay, so I intentionally let you fall into this problem just so that you understand that when the CPU calls this function, right, then it doesn't wait for it to finish, right? You're just posting requests to the GPU to run that kernel. So basically what you're timing here is not the time it takes to run the kernel, but just the time it takes to request that the kernel is run. So this returns immediately, basically, for all intents and purposes. This GPU AXPY returns immediately, which is why you see this huge bandwidth, right? Because you're not really timing the time it takes to run the kernel. What you want to do is you want to wait for the kernel to finish and then record the timer, because that will reflect how long it takes to run GPU AXPY. And so what you can do is call this CUDA device synchronize command immediately after you call the kernel, and that should, you know, wait until the kernel finishes before it calls stopwatch again to get the time, right? Okay, so this is useful to know because sometimes you want to use this to, you know, this is a feature, right? Not a bug. You want to be able to send things to the GPU and then do other things on the CPU while those kernels are being run. This is how you do it, and then you synchronize afterwards, right? Okay, just to note that the CUDA memcopy is also a synchronization command implied, right? So if you do a lot of kernels, if you post a lot of kernels, I mean, here we're just posting one, but if you queue a lot of kernels, so if you have another program where you have a lot of kernels, and then underneath you do a CUDA memcopy, then that will implicitly tell, you know, that implicitly says to the CPU to wait for all the GPU kernels to finish before doing the CUDA memcopy. Okay, that's just a note that you might, you know, use again in a real application. Might be useful to know.
Basically, the CPU goes to the next line.
Yeah. It just dispatches the kernel and then comes back immediately. Okay, so now I added this synchronize command. And okay, this looks more realistic. The bandwidth is very small, right? Does anybody remember what was on the slide for the bandwidth of the GPU? What was that? 130 was the CPU. This is closer to a terabyte per second, okay? So about 900. And we are getting here 0.2. So we have some way to go. This difference is not 0, but is 10 to the minus 15. So this is floating point precision, okay? So that's okay. So we can consider that the result is the same, right? This is not exact, as I said, this is not exactly 0, but we're using floating point arithmetic. So this should be good up to, you know, 10 to the minus 15. Okay, so what to do now? I mean, we're not getting what we expect in terms of how fast the CUDA kernel should run. So what can we do? Well, the first thing to note is that we're using only one GPU thread, of course, right? And the power of the GPU comes from the ability to use a lot of threads in parallel. So why don't we use, say, 512 GPU threads, right? Sure, we can do that, right? So what does this mean? It means that we come here. Remember, this is the number of blocks, and this is the number of threads per block. And now we're just using 1 and 1. So that's, as we said, this is definitely not optimal. So let's use a lot of threads. So 512 threads, for example, okay? Remember, the upper limit is 1024. We're using 512. Well, if we just stay here, we haven't done much. Actually, we've done worse than we did before, because all that means we've achieved is 512 threads will do exactly this thing. This is pointless, right? Because they will all do the same operation from 0 to n minus 1. What we want to do is we want to distribute these n iterations between the 512 threads, right? So we want to go into the GPU kernel and find a way to spread the work around these 512 threads. So what we want to do is first to identify which thread is running this kernel, right? To get the thread ID. And based on the thread ID, determine which part of this array is going to be computed by this thread. So this is not a unique thing, but one way to do it is what I wrote there. So you have 512 threads, right? So one thread will be thread 0, one thread will be thread 1, another thread will be thread 2, etc., up to the thread with thread ID 511. So you have 512 threads with a unique ID, and you need to find a way to distribute this array, which is of length n, between these 512 threads. Okay. So first thing we want to do is we want to capture the thread ID. So we have one block. Remember, we have, I'm going to go back again to this picture here. Okay, so we have one dimension now, not two dimensions. So we just have one row. We don't have any columns. So we just have one row. We don't have any rows. We only have columns. And we only have one block. So it's all within one, one of these green tiles. And so a thread is uniquely identified by thread idx.x. Okay? This just uniquely identifies all the threads because we only have one block. Going back now. Yeah, here we are. So that's what we capture here. Thread ID, what I call iThread here, is thread idx.x. Okay. So we captured thread idx. And we also want to get the total number of threads. That's also useful to know. So the total number of threads, which in this example is this number 512, the way this is passed down to the kernel is this block dim, right? So this is exactly what block dim is. It's the number of threads per block. Okay, so to recap, this code here will be run by 512 threads because I asked it to, right? I put 512 down there. ITHR, the variable ITHR, will be unique for each thread that will run this kernel. For the first thread, it will be 0. The second thread will be 1, up to 511. And NTHR, and number of threads, right, will, for all of these 512, have the number 512, right? I'm passing down the number 5. Okay. Yeah. Oh, yeah. Because that was the number of OpenMP threads. So I've removed it from here. Yeah. Okay, and so now I want to break this loop up to these 512. So I want thread 0. Well, no, let me do this. So how many elements of these n elements does each thread need to go over? Well, I'm going to call this, I think on the slide it's LT. So this is just n over n threads. And by the way, when you do that in your codes, you don't do what I do here, right? You don't do as I do, but do as I say. So you don't do this. You check that n is divisible by n threads, and you do take care of some. But okay, here I'm, this is more better, as a training exercise. Maybe it's okay. So yeah, that's what I have here. So so now I have this LT, which is the number of iterations that each thread will do. And I want thread 0 to go from 0 to LT. I want thread 1 to go from LT to 2 times LT. I want thread 2 to go from 2LT to 3LT, right? So basically, this should do what I said. So maybe I give you 5 seconds to look at that and convince yourselves that it does what I want. If it's thread 0, then it'll go from 0 to LT. If I thread is 1, it'll go from LT to 2LT, etc. Right? And so each thread is taking the portion of these n elements that corresponds to it. Are we good? Is this clear? It's clear? Very good. Very happy. Compile. And let me just make sure it's, so I get compile and run. And remember okay. So you see that the difference is exactly the same as before. So we haven't changed anything in the results, right? So even though we're using 512 threads, the difference between the computation on the CPU and the computation on the GPU is exactly the same as before when we were doing this with one thread. This number here is identical to my previous rundown there. Is it faster? Yes, it's faster. So this was 0.2 gigabytes per second, right? The speed at which it did this. I mean, we can just look at the times rather, if you don't want to look at gigabytes per second, you can just look at the time. Here it took 3.5 seconds, and now it takes 0.2 seconds, right? So this is obviously faster by more than a factor of 10. It's faster by more than a factor of 10, but it's nowhere near where we expect the GPU performance to be if we know what the bandwidth to memory of the GPU is, which we said is close to a terabyte a second. Okay, and that's when we talk about the first thing, which we should, and that is about how the GPU accesses memory. Okay, so this is perhaps the most important thing you should leave from here with you to keep in mind if you ever need to do this kind of GPU, low-level GPU programming. So what I show there in the picture is the order by which the threads access the data in the array as it is now in your code. Okay? The same thread, so let's say thread X, I don't know, thread 0, whatever, accesses a chunk of data continuously, right? This is a very common approach of how you would program a parallel implementation on a CPU. This is how you would do it, right? This, if you're familiar also with OpenMP, this is what you do. A thread gets a chunk of memory, another thread gets a far away chunk of memory, etc. On GPUs, this is the opposite of what you should do. Okay, this results in these so-called bang conflicts. So the memory on the GPU has a very specific access model, which is sort of so-called banked, which just means that, you know, there are banks that are used to access memory from the threads, and this is more optimally done if continuous threads access continuous elements in memory. What that would mean in this specific example is, and it's showing it here, so before, this is the array 0, 1, 2, 3, and these are the threads 0, 0, 0, 0, 0, then 1, 1, 1, 1, 1, right? But you want to sort of transpose this, okay? So you want thread 0 to read element 0, thread 1 to read element 1, thread 2 to read element 2. At some point, you'll run out of threads, right? Because the number of threads is less than the number of elements. Then you start off from 0 again. The further away these elements are, the better, okay? To avoid these bang conflicts. So we need to turn this around. And one way of doing it is what I wrote there. So let's go through this. Again, you get the thread index, you get the number of threads with n thread. And now what you can do, as I said, this is one way of doing it. You can iterate this jumping by n threads rather than I++. You can just go n threads at a time. And then you replace the index with I plus n thread. So make sure that this is convincing that what I wrote here actually implements what is on the previous slide. Okay. So let's see what happens when we use this. Compile again. And run. Okay, so this indeed is faster.
Excuse me?
Yes?
Can you repeat why it is much faster?
Can you ask again? Sorry.
Can you repeat why it is much faster?
Not really more than I already said. So, I mean, I can't get into too much details without getting too technical, but suffice to say that the way the memory is laid out on the GPU, right? Sort of at the hardware level, the way the memory of the GPU is laid out is such that having each thread access nearby pieces of memory is more optimal than having the same thread access nearby pieces of memory, right? It's just the way that without risking of getting too technical about, how the hardware is, it's just as a rule of thumb, you should always aim to access the memory with the threads in this pattern rather than the previous pattern. That might not be very satisfactory as an answer, but
Thank you.
Yeah.
Thank you.
Okay, so what do we have here? On the slide, it says that this got up to about 12 gigabytes per second, or about 0.06 seconds. And yeah, okay, that's about what I also got now. So this is still fast. So this is still faster than before, but of course not as fast as we would like it to be, especially given that this is still slower than the CPU, right? When we expect this to be faster than the CPU. So what is the last thing we can do? Well, the last thing we can do is actually use blocks. So far we're using one block, right? We have 512 threads and we're using one block. And what we can do is basically we can use an arbitrarily large number of blocks, right? So you should assume that there's no limit on the number of blocks you can use, right? The real limit is some huge power of 2. So what we're going to do is something which is very common in such GPU programming, is we will basically assign one thread per element. So no loops. There's no need for a loop anymore, right? Just assign as many blocks as you need to completely pad the array with threads. So if you're going to use 512 threads, then how many blocks do you need to have as many threads as there are elements? N over 512. Those many blocks, right? So here's an example here where I use the maximal number of threads. Here I use 1024, for example. And then I use N over 1024 blocks. So there are as many threads, again, there are as many threads as there are elements in the arrays that I want to compute, which means that I can uniquely identify which element the thread will operate on by the index of the thread, right? So first of all, let's do this. We go down to where the kernel is being invoked. Right. So n thread number of threads per block, and as many blocks as I need to have one thread per element of the array. Yeah, good. And then, but then I have to go up here and change something. So first of all, I don't need a loop, right? So no thread needs to do any loops now, because it's just one thread corresponds to one element of the array. So there's no loop, no need for a loop, right? What I need to do is just get a global thread index, right? Not the index of the thread within the block, but the index of the thread within the whole of the group of threads that the grid of threads that I'm using, and use that as the array index. So this you can compute here, right? Like this. And then IDX is this unique ID, which goes from 0 to number of elements in the array. File. And run. Okay, so now we're talking. Right now we got something like 720 gigabytes per second. This is at least 7 times, 8 times faster than the CPU. And it's close to the 900 gigabytes per second, which NVIDIA tells us is the peak bandwidth of this device, this GPU, right? So we're getting, again, a similar percentage as the CPU, about 80%. So here we can be confident that now we're sort of approaching the limit of how fast we can do this operation. Okay, so the way I designed this here is I can change the number of threads here, right? I can change this end thread. I can't make it larger because the upper bound is 1024. I can make it smaller. And as long as this divides the total elements of the array, then this should still work. It will just change accordingly the number of blocks that I need to pad the whole array. And just like to say that maybe 1024, this maximum, is not necessarily the optimal. You could get small differences by tweaking this number. So for example, if I try 512, that this might be a bit better. It depends on the problem. Yeah, here it's a bit better. Okay. I can try 256. It would be even better if I could pass this as a variable, so I don't need to compile each time. Yeah, so this is, so yeah, okay, so the sweet spot seems to be 500. Okay. Let's just reproduce that. Okay, so it fluctuates also from run to run. But I hope this gives you an idea of at least how one goes about distributing the work between GPU threads, at least when you have these kind of simple operations. Okay. Yeah. That's also what I got when I was making the slides. Okay. This was the main part, and I have a second example that probably we won't have time to finish here, right? But I can explain it to you. You can start it off here if you want. But it I sort of explain to you what the main idea is. So there's a second example which is similar to this one, which is just to test whether you can take a similar program of this one, so one that runs on the CPU, and then move it slowly to the GPU, but now without me doing this for you, step by step, but you need to do a few of the steps yourselves. So before I go to that, are there any questions that you want to ask about anything I've said so far, or something to repeat? So is this all clear? Like what we did and how we got to this point? Okay. Anything you want me to repeat now? Yeah.
I work as compare nowadays running CUDA cluster versus now with clusters over there. So it's just another cost. Or do you feel there are performance in which instead of knowledge you work without you work from there?
The question is related to if I can comment on the performance of running something in a on an in-house sort of GPU cluster compared to running on the cloud. Yeah.
It's just a matter of what hardware aim for once they go on the cloud and they get better results for new things that are advantages which with the cloud itself we cannot achieve unless we
So I'm assuming you're asking if you go to a GPU solution on the cloud, right?
Well, I guess the point is compared GPU solution for the cloud that is it for itself. Which kind of GPU? But if I don't use GPU solution on the cloud, I'm using just a cluster of startup
Oh.
Think I can get the same results or not. I don't know if maybe that makes sense.
Yeah. I mean, I don't think anybody can give you a general answer without being problem specific about this, right?
And this probably means that if I get the correct type of infrastructure of cloud, I can get the correct results. So there is nothing that to get the same result I can get on the on-premise GPU-based cluster that I can not achieve.
But this is always a function of how long you're willing to wait versus how much you're willing to spend in both cases. And it also depends on what you're running, right? So there are examples of applications that don't map well to the GPU architecture, right? They just don't map well. And so regardless of if you're doing this in the cloud or on a workstation, using the GPU might not be the right way to go to solve this problem. Whereas in other cases, problems map well to GPUs, and depending again on how much time you're willing to wait and how much you're willing to spend, it might be more cost effective to run this on a GPU that you have on a workstation compared to, allocating 100 cores on the cloud. Yeah, I mean, this is not a satisfactory answer, but it.
That there is not something specific that will tell you to give up on your premise GPU, then you will never give it to that. So there is nothing that technologically.
No, but what? Well, but okay, but why are you giving up your on-premise GPU? Presumably, you don't want to be. Okay. Yeah.
On this code, I may choose to ask, for example, you to give me a login to the cluster.
Yeah.
Versus, I go to the cloud service provider and I spin up the Spark cluster and
that's great.
I run it there.
That's a great question. I would say I'm not the best person maybe to talk to about this, but I say that's why we're here, because we know that this is specific to your problem. You should talk to, I can bring you into contact with people that can actually sit with you and help you decide based on your application, whether it's better to, you can get a test account here, you can run your code here, you can then also run it on a cloud and then make the decision, right? So part of our job is to actually give you the information you need in order to decide this for yourself, but this is not knowable a priori, right? It depends on the problem. But yeah, thanks for that question. Any other questions? Okay, then I will move on to this to this second exercise, which, okay, this is a bit more, this exercise is similar to the previous one, has a bit more of a twist, let's say, at the end. But I can spend some time now to explain what it is, what you need to do to solve it, and then, you know, feel free to try it and come back to me, and I can, you know, provide the solutions in the next day or days so that you can check what you do. So this is exercise 02/rot.cu. So what this, well, I mean, the operation that is done here is rotate and shift operation. Okay, so basically you have an array of two-dimensional vectors, so an array of an x and a y coordinates. And what the program does is each element of the array is an x and a y coordinate, and what this program does, it rotates by a specific angle the array at each element, and it also translates it by a given vector. So the rotation is constant, and it's called a u here. And you know, if you want to rotate a two-dimensional vector by an angle theta, then you know you apply this two-dimensional transformation matrix. I hope this is familiar to at least most of you. So yeah, so if I have an x coordinate here and a y coordinate here, then you do, you know, cos theta times x minus sine theta times y, and that will give you the x coordinate of the rotated matrix, and you sine theta times x plus cos theta times y, and you get the y coordinate of the rotated matrix of the rotated array. This is here, and then I also shift. So if what I said to you sounds foreign, then I don't, you know, what you need to know is basically that you're just doing this operation and this operation in a big loop for I going from 0 to n, right? This is very similar to the previous operation. If you just, I mean, this is sort of a generalization of the previous operation. So previously we had, you know, some a times x plus a vector, where now this is a bit more, you know, it's a bit more complicated, but it's still like a scale and a shift operation. Okay. So, I mean, visually, just to visualize this a bit. So, I mean, in what we're going to do, you have, so here there are 4 points on the circle, the 4 points, right, in this coordinate grid. But what is done in the exercise is like millions of these points, but just to visualize it. So this is equivalent to, you start off with some points like this. You apply this rotation, so all of them rotate by the same angle, by some amount, right? Same angle. So they end up there where the red points are. And then when you add this S, you're also shifting them by some random, and then you end up where the green points are, okay, to the new coordinates. So you start off by R, and you end up with V so R and S are the input vectors, and V is the output vector of this operation. Okay, this is implemented in rot.cu. So similarly to what I did before, I will copy exercise 02 to this directory. And note that now, if I cd into expert2, there is the CUDA file, right? But there are also 2 other files. those are just files that will be read in by this C program. So points contains the coordinates of R's, the R, and shifts contains the coordinates of the S. And just like before, this program now does everything on the CPU, okay? And it does it twice. Does it twice. Let's just look at this real. Oops. You can see that, right? No. Okay. Okay, sorry, but I have to. So those who are not very familiar with C have to excuse me, but I'm basically using something which is called a structure in C. This is like an array, but where the elements of the array are named, right? So now you have a .x element and a .y element. So this is this core. This is just simplifying a bit the program. Let me skip some of that stuff and just go to main program. Okay. So again, we take from the command line a number, which is just how many elements we are going to do. It's just that these elements now are read from a file. So this n has to be smaller than the size of the file. And on the CPU, again, there's no GPU code in this program at the moment. On the CPU, we allocate R and S, and then we allocate two arrays for the results, for the resulting V, right? There's V0 and V1. So R and S are read from these files here. The angle is 10 degrees. It doesn't matter what the angle is, right? But it's 10 degrees here. And then you call rotate. First time here under A, you call rotate V0 theta R S. Okay. And then you call it again and put it in V1 this time. And then V0 and V1 are compared. Is it? Yeah, here. Okay, it also writes it out, but that's not necessary. And if you want to see what this rotate function looks like, so the cosine of theta is pre-computed here, and the sine of theta is pre-computed here, just so you don't have to put them here inside the main loop. And then this is the operation that should map one-to-one what I have on the slide here at the top, right? Okay, so what I write here should be identical to what is done here in the code. Okay. So it's so what you need to do now, what you can do is just go back. Hopefully, you can go back to how we started with the AXPY, or this AXPY, and all of these steps should map very nicely to how you would go about now transforming this new code, that exercise 2, in order to run on the GPU. I realize we only have 30 minutes, so if you need to leave, then I understand. But if you don't, then I'd be happy to stick around, and you can try and do this and see how successful I've been in relaying the message in the previous one. Oh, I mean, before you start, hacking away, when of course what you can do is compile this as it is, just make sure it works, right? Yeah. Όχι, αλλά έχουν τον το hip που βασικά όλα τα CUDA functions ξεκινούν που hip. Εν όλα τα CUDA functions απλά αντί να ξεκινούν που CUDA, ξεκινούν που hip. Βασικά η AMD έκαμε implement βασικά το ίδιο API που κάτω είναι διαφορετικό φυσικά, αλλά τα function names είναι σχεδόν τα ίδια. Και μπορείς απλά να αλλάξεις και να... Αλλά αν κάνεις κάτι complicated, έχει πολλούς κώδικες που κάνουν πράγματα που είναι πολλά specific σε NVIDIA, δηλαδή χρησιμοποιούν πιο low level πράγματα. Και είναι πιο δύσκολο να κάνεις map στα AMDs. Αλλά το σκεπτικό είναι το ίδιο, δηλαδή η overall architecture. Ναι, καλά. Ναι, πιο... Κανονίζεις σου τα γίνοντα copies και τα ξέρω. Well, yeah, okay. Φαντάζομαι γιατί για να μπορείς να κάνεις εύκολα switch σε CPU.